Thanks everyone for coming here. It's my pleasure to introduce my friend and our speaker today, Dr. Henrik Ardenkjaer-Larsen from the Technical University of Denmark. And Jan received his PhD from the University of Denmark on Overhauser MRI. And since then, he had a very interesting career path. And early in his career, he worked for Emerson. And among many projects there, he worked with Dr. Claes Goldman to develop dissolution DMP technology. And in collaboration with Oxford Instrument, they actually produced the first commercial version of the dissolution DMP polarizer, and that is the Hypersense. And we have a Hypersense in the Boston area, and Aaron Graham is the PI from BIDMC, and he's here with us today. And then in 2004, GE Healthcare acquired Emerson, and Jan stayed working with GE Healthcare, continue the development of this technology for clinical research purposes, and they produced a commercial product that is the SpingLab, and that's designed for the clinical research by using this technique. And then and in 2015, he returned to academia. He's now a full professor in the Department of Health and Technology. And he's running a big lab. He's the head of the Center of Magnetic Resonance, and also leading the Center of Hyperpolarization in Magnetic Resonance, which is the Center of Excellence funded by the Danish National Research Foundation. Yeah. He's the brain behind all the commercial DMP polarizer, and now he has his own company, and he continues developing the next generation polarizer, which we will learn about today. And Jan has an impressive 28 patents, 125 journal articles, and he is a recipient of numerous awards, including a recent gold medal award from the World Molecular Imaging Society in 2014. And in addition to the research excellence, Jan is also an avid marathon runner. Do you remember how many marathons you have run so far?
How many?
How many? Yeah.
10, I think. So.
10 also. Okay. All right. Hopefully you will come again to run the Boston Marathon.
I did that. I did that. Yes.
Okay. Excellent.
Yes.
Okay. Which year was that?
2 years ago.
2 years ago. Okay. All right.
Yeah.
Okay, that's awesome.
2:42 is my personal best.
Okay. Well, that's very impressive. Very impressive. Yeah. Well, Jan is going to talk about hyperpolarized MR today, and without further ado, that's a welcome speaker.
Okay, well, thank you very much for the kind introduction and the invitation to speak. I'm very happy to be here, and it's been a really wonderful day today, yesterday. Yes, can you hear me at the back? Yeah, okay, good, thanks. Yes, I'm sure that most of you are not familiar with the topic, so I divided my talk into different parts. I'll give you an overview of the field, try to give you an introduction to hyperpolarized MR, hyperpolarized metabolic MR, and then I'm also going to dive into a couple of subjects that are close to my heart and is also going to affect you to some extent. As Yifan mentioned, you're getting a hyperpolarizer yourself here at the Martinos. So that's the content of the talk. Yifan already gave a lot of the background to me, so I'll skip the introduction of myself. Just first start with a little bit of the background for the project. We actually, before we found ways of hyperpolarizing, we sort of, from a long track record of looking at new contrast mechanisms in MR, started to think about, well, MR is a fantastic, beautiful modality, imaging modality, as you're fully aware of. We have these beautiful anatomical images with a lot of nice soft tissue contrast. anatomy, morphology, function is very well depicted in the MR image based on the water proton signal. But magnetic resonance has so much more to offer. We can get molecular fingerprints, we can get an MR spectrum that gives us identity, quantification of metabolites. However, in the case of the clinical MR, we really struggle to enable that. So as we know from proton MR spectroscopy, we have coarse resolution images. We can detect the most abundant metabolites. We need long scan times. And when we go to other nuclei, let's say tracer or molecular imaging variants to that and infuse carbon-enriched substrates, we basically lose all the spatial resolution, and we need to average for a very long time, but we can then see the incorporation, the degradation of the substrate, and incorporation into products over a long time course. But we basically have very coarse temporal resolution and very coarse spatial resolution. So our thought was that if we could just enable that and we could add this biological molecular information on top of the beautiful anatomical information, we would have a fantastic tool in order to characterize disease and understand the biochemistry, the biology behind disease progression and treatment response and similar things. So that was the thought. We then had to find ways of improving the sensitivity of magnetic resonance, and that's really what we enable with the hyperpolarization. That we know that we have poor sensitivity in magnetic resonance because we have a very poor polarization alignment of the nuclear spins with the magnetic field. So we know that the signal, our magnetization, is proportional to the concentration times the polarization of the nuclear spins. We are now moving down from 60, 80 molar water protons to millimolar concentrations of metabolites. So we lose 5 orders of magnitude in the concentration. So we need to compensate that in some way. And we can do that by increasing the polarization. When we put an object, a person, in the MR scanner at room temperature, well, the nuclear spins are only very weakly aligned with the magnetic field. So basically, we have a parts per million alignment. All the nuclear spins are almost randomly oriented. That's because the resonance frequency is in the megahertz range. That's the magnetic energy compared to thermal energy, which at room temperature kBT is 6 gigahertz, so 6 order of magnitude bigger, which means that the Boltzmann factor is really poor. We can, of course, reduce thermal energy by cooling the sample, cooling the spins, so we can reduce the temperature. We can apply the strongest magnetic field we have, and that improves on the Boltzmann factor. We can also use a technique called dynamic nuclear polarization, where we exploit that the electron spin has a much higher magnetic moment, 1,000 times bigger than the nuclear spins. So it's much easier to polarize electron spins. So if we take a radical or an electron spin, put that in a magnetic field and reduce the temperature, then as we go down in temperature and we approach 1 Kelvin, then the electron spin is almost fully polarized. So now we have electron spins with almost unity, 100% spin polarization. Now we can use DNP to transfer that polarization from the electron spin to the nuclear spins by irradiating at the electron spin resonance frequency. So in a solid state at low temperature, we can create a solid material with almost fully polarized nuclear spins. Now the trick is then to formulate that in a way that we introduce it into the patient or the animal. So now we introduce the dissolution part of it. We do a very quick temperature jump phase transition. We dissolve the solid material in an aqueous buffer and very quickly. And then we end up at room temperature with a liquid solution of the hyperpolarized spins, molecules, and now they relax back to thermal equilibrium, but before they do so, we inject it into the animal, into the patient, and we use the high signal to image the substrate and metabolites. That's a huge factor of 10 to the 5th. compensating reduce the concentration. And you see here the example of that. We have the electron spin and the polarized nuclear spins. And if we do this hyperpolarization, we put our hyperpolarized sample in the NMR spectrometer, we can acquire an NMR signal in a single scan with very high signal to noise. Same sample scanned over the weekend gives a very poor signal to noise. So it translates into a huge improvement in sensitivity, reduced scan time. So that's exactly what we need to do real-time metabolic imaging. So where does the electron spin come from? Well, it's typically a stable organic free radical. You see some examples of it here. It could be nitroxides, it could be BDPA, trityl radicals, but these are organic molecules with an unpaired electron spin. We do chemical doping into our biological molecule of interest, and that's the source of the electron spin. We could also use transition metal ions. Some of them have very narrow EPR lines. So here you see examples of EPR spectra of these paramagnetic agents that we can use. They're all good polarizing agents for DNP, but you can see that they have quite different EPR spectra in terms of width, and that determines how efficient the DNP mechanism is and which type of DNP mechanism that we exploit. You can see here that when we look at the proton DNP or carbon DNP, then you can see that these we call microwave spectra, that as we change the microwave frequency to irradiate on this electron spin resonance, and we get positive or negative enhancement. You can see that we can get a very strong negative or positive very well resolved. That's called the solid effect. So there are different DNP mechanisms that can be effective. And just to give you a short introduction to DNP, then in the solid state, we have the electron spin from the radical. We have the nuclear spins in our bioprobe in the matrix in general. They couple dipolely, so we have pairs of protons, carbon, and the electron spin that where we can induce, due to the dipole coupling between this pair of spins, we can induce transitions between this pair by irradiating with microwaves at the sum or difference frequency, which is typically in the microwave range, and then do spin flip-flops. And then this is a local mechanism. So the polarization of those local nuclear spins then diffuses into the bulk of the material, and that way we can polarize generally all the nuclear spins in the solid material. There's also another mechanism which is more effective under the conditions that we work at, which involves two electrons. So you can have a pair of electron spins that resonate at slightly different frequencies, with a difference frequency corresponding to the nuclear llama frequency, either a carbon or a proton. And by inducing three-spin transitions, we can then polarize the local nuclear spins, and then again by spin diffusion, that local nuclear spin polarization diffuses into the bulk of the material. So DNP is very efficient in terms of polarizing generally nuclear spins, and also very general in terms of polarizing many different biomolecules. So this is how DNP works very quickly. So you need, in order to do DNP, you need a strong magnetic field, you need low temperature, as I just indicated. So this is just a very schematic of the first of the prototype, which gives you the key elements of a DNP polarizer. You need a superconducting magnet to generate these 3 Tesla, 5 Tesla, 9 Tesla, some relatively high field strength. Then you need to create a low temperature. So in this first design, it's a normal NMR magnet with liquid helium, liquid nitrogen. We can use the helium that cools the magnet to drain that into the sample space and fill that with liquid helium. To get to the low temperature that indicated the 1 Kelvin, we need to pump on the helium. Helium's boiling point is 4.2 Kelvin, but if we pump on it, the boiling point is reduced. So that way we can reach 1 Kelvin. So these mechanical pumps is just pumping on the helium. We have the sample immersed in liquid helium. We radiate with microwaves, not very much power, but in the hundreds to 200 gigahertz range, depending on the magnetic field strength. And then DNP takes place. We polarize the solid material. So now we have to dissolve it. So we take what we call the dissolution stick, put that into the cryostat, connects it with our sample. And then we have boiling hot water that we inject in order to dissolve the sample. And then we have a hyperpolarized solution flowing out of the cryostat. this was the original design, and as Yifan mentioned, GE licensed the IP to Oxford Instruments. They built the Hypersense, which was very similar to what I just described. They sold about 50 systems of those, so they're around the world, mainly doing small animal research. Oxford Instruments discontinued that 5 years ago, so there's really no source of polarizers at the moment, except this new thing, which I'll talk about later. GE took one of the original prototypes, put that in a clean room at UCSF to really accelerate the clinical translation and do the first patient study. So I'll give some data from that. So that's the clean room installation of UCSF back in 2007, 8, 9, those years. That was a full clean room installation. So in parallel, GE developed what we call the spin lab, which doesn't need the clean room installation. And today there are about 25 spin labs around the world. 10 sites have approval to do human studies. So we started to get quite a lot of patient data in different patient populations. My interest is very much around the technology. So I continue to develop polarizers that are still, it's a rather complicated technology, as you can already imagine. So we try to get around some of the cryogenics and other elements to make it a more practical and affordable in a clinical setting. So this is a polarizer that I'll talk more about, latest generation. So just very quickly, a video just describing how it works. This is from Oxford Instruments. Damien Tyler got one of the first prototypes. I built that for him. Second, you see the two PhD students have just been polarizing. The sample is in the cryostat down here. This is the dissolution stick. The hot solvent has been heated. Now the sample is just lifted out of liquid helium, and they can introduce the dissolution stick, release the solvent, collect the hyperpolarized solution, run to the MR center, and the clock is ticking. There's a rat in the scanner with a tail vein catheter injecting now the hyperpolarized pyruvate into the bloodstream. It flows to the heart. This rat has a coil on the chest. They are looking at cardiac metabolism. You see the hyperpolarized substrate, and then you see all the metabolites of pyruvate appearing in real time on the NMR scanner. So this is how it works in the prototypes. But as you can imagine, time is clicking. This is a non-equilibrium state that we're creating. It's relaxing quickly back to thermal equilibrium. The signal is decaying. In the NMR relaxation times are short. If we do clever labeling, clever selection, or labeling positions, we can try to extend that time window, that decay time constant as much as possible. It can be a minute or two. But you can see here that when we do an intravenous injection, the substrate has to flow with the bloodstream to the organ of interest, the reach of interest, has to be transported into cells and metabolized. So the biology has to be very favorable. Within that time window of 1 to 2 minutes, of course, there's a limitation to what kind of biology we can interrogate. So naturally, we're looking at energy metabolism and substrates that have high transport mechanisms and enzyme activities. What we knew back then was since we are injecting relatively high concentrations, we knew that, let's say the pharmacokinetics would be relatively favorable, that if when we inject the bolus, we know that blood circulates to the organs of interest within that time frame, but we didn't know much about the biology and what substrates we could actually use within that time window. But that is a limitation and a consideration. Just very briefly, as I mentioned, DNP is very general. It's not it was invented in the 50s, so it's been used to polarize nuclear spins in many situations in various ways. But since we need to have a relatively long relaxation times, the nuclear spins that we are interested in for dissolution DNP are spins 1/2, spins that have long relaxation times. And you see them all highlighted here in this periodic table. Since we're interested in biology, we also naturally focus on carbon-13, nitrogen-15, to say the building blocks of organic molecules and biological molecules. So these are natural nuclei to focus on. Carbon-13 has a low gamma and a low magnetic moment, so it will also, for that reason, have long relaxation times compared to the protons, which are not very good for dissolution DNP because of the generally short T1s. The compounds that we have that have been studied is Some of the most interesting, this is a selection of substrates that have been studied, but just to give you a flavor of what we could study, as I mentioned, we need long relaxation times, we need fast transport, fast biology, so naturally we focus on small molecules, intermediates of energy metabolism. We need to, and I'll get back to that in a minute, we need to cleverly select labeling position, but just to give you a flavor of the biology, there are pyruvate is one of actually the molecule that has been translated to the clinic. That's the end product of glycolysis. It's very central in energy metabolism. Fumarate is an intermediate of the Krebs cycle. Fumarate to malate is a mark of necrosis because fumarate, as it leaks out of the cells, will convert the fumarate into malate. Bicarbonate, dehydroascorbic acid, acetate, another keto acid, ketohydrochlorate, amino acids, carbohydrates. So these are the type of molecules that we can enrich with carbon-13. We can hyperpolarize, and where the biology is favorable, that we can see products in the breakdown of these substrates within that time window of 1 to 2 minutes. Now, I'll use pyruvate as an example because it's a molecule that has been taken to the clinic. You see here pyruvate, a 3-carbon molecule. There are 2 obvious labeling positions for pyruvate, the carbonyl and the carboxylic acid, because we have no directly attached protons. So the relaxation time, the T1 will be long. The methyl will have a short T1 because of the attached protons. If we label in the C1 position, then if pyruvate goes into the Krebs cycle, we will lose the carbon as CO2, and which is in equilibrium with bicarbonate. Pyruvate can also be reduced to lactate, or it can be transaminated to alanine. So this is a known biochemistry, the textbook chemistry of pyruvate. The NMR spectrum will tell us, based on the chemical shift difference, how much of the pyruvate goes into lactate, alanine, and bicarbonate, so we can quantify that in the NMR spectrum, and we can make images of the product, which is really the unique feature of magnetic resonance. Yes, and as I mentioned, pyruvate is the end product of a glycolysis, it is very central in the energy metabolism, and really from a biology point of view, what we're exploiting with pyruvate is that cancer and other diseases, but let's stay with cancer, that we have a higher energy metabolism and an elevated aerobic glycolysis, the Warburg effect in cancer. So we know that the tumor, you see an example in a rat, the tumor here on the stomach, that there's a higher uptake of pyruvate, increased expression of monocarboxyl transporters, so there's a higher uptake of pyruvate into the tumor, but also that we see an elevated aerobic glycolysis, beautiful demonstration of the Warburg effect, that there is a reduction of the pyruvate to lactate, and we see this lactate in the tumor as we should expect. So a demonstration of the Warburg effect. Now to the clinical part. So again, Luis focused on cancer and specifically on the prostate cancer, prostate cancer population. So this is the first GE-sponsored study at UCSF, 31 male patients included. First, we wanted to know something about the timing of the metabolism and uptake of pyruvate. So this is just spectroscopic mode with 2 slices interleaved between the normal region of the prostate and the part of the prostate where we can see anatomically can see the tumor in the proton image. In normal prostate, we see the arrival of the pyruvate. You can see it's very fast from the IV injection in the arm. 20-30 seconds after the injection, it arrives in the prostate. But in a normal prostate, no production of lactate, no lactate signal. The slab that goes through the tumor, we see again high pyruvate signal, but very short delay as the production of lactate in the tumor region. So now we have the timing and the confirmation that it is produced by the tumor and not by the normal prostate. So now we can move on to do imaging, mapping of lactate. So here's an example of another patient. Again, we see here in the proton image on anatomy, we see clearly on the T2 weighted image, the dark area, the tumor region. But in this case, in the pyruvate map, we see the strong lactate signal in the tumor as expected. But in this case, they observed bilateral cancer in a region that was not detected in the proton image. So it really shows that the information we have in the anatomical image is not sufficient to detect all tumors. This patient was on active surveillance and went on radical prostatectomy, so it actually had an effect on this patient, but really was a proof of principle, proof of concept.
Is there higher signal to noise for this than there would be for just imaging lactate using proton spectroscopy?
I believe so, yes. I'm not sure that you can do lactate imaging. I think it would be hidden by the lipid signal. So I don't think you can image lactate by proton MR spectroscopy in this case.
Well, there's ways.
The SNR?
No, I mean, saying it's easy to get rid of lipid signal using just a stir technique or something like that.
Okay. Possibly, yes. That's a good question. I haven't seen anyone do that, so wouldn't be able to say direct comparison. UCSF continued in another study trying to correlate that lactate signal with the staging of the disease, so including more patients with different grade stage of the disease. And the lactate hotspot that we saw in the image correlates very nicely with the stage of the tumor. And also looked at the therapy response. So this is another study with a patient that has a very large tumor, which was not responsive to treatment, but went to hormone therapy, androgen deprivation. And before the treatment, a very strong lactate signal indicating aggressive tumor. But it turned out that this patient was a responder, and 6 weeks post-treatment, the lactate signal is completely gone. So very nice demonstration that we can use the lactate signal to monitor response to treatment and discriminate responders from non-responders. So I think the basic biology is well demonstrated. The vision of the method was well demonstrated by these examples and this preliminary proof of concept data. So I think I can say that within the field of hyperpolarized metabolic MR, that we have it still meets the original expectations that we have demonstrated in these proof of concept studies, that we can actually stage disease, we can monitor response to treatment, that we have been able to make the clinical translation, that there's now a number of systems installed around the world that could do, where many have approval to do human studies, and there are a number of publications that have come out in the recent years in different patient populations along the lines of what I just illustrated in these examples. So now I want to talk a bit more about polarized technology, because you are getting one here. So this is the preclinical polarizer that I've been developing, which is really meant as to enable researchers to do animal research. This system is very different from the previous systems by the fact that it's a dry magnet. It doesn't consume all the cryogens that the previous systems do, because that is one of the limitations that what I showed you earlier in the video and first design uses a lot of liquid helium, which is scarce and expensive and impractical. So we have been moving to a cryogen-free system. So this magnet is cooled by a cold head, just like your MR scanner, that provides all the cooling power. We want to operate at a very low temperature, so that's a challenge. The cold head can break it down to 4 Kelvin, make the magnet superconducting. It provides all the cooling power of the system, but we need to go lower in temperature. So we still have a helium system where we have a little bit of helium gas on buffer tanks, and that helium gas can be condensed by the cold pad and liquefied. So we have a small volume of liquid helium. We can still drain that through a needle valve into the sample space, pump on the helium to get the temperature down to the 1 Kelvin, but the exhaust of the pump go back to the buffer tanks, and then it's a recirculating system that doesn't consume any helium, but we can still bring the temperature down to the 1 Kelvin. We are on this preclinical polarizer, we are still using the same fluid path as we do on the spin lab. So the sample that goes into the cryostat is put into this little vial. The solvent is put on a syringe, and then this syringe is heated, and we can inject solvent to dissolve the sample, and then it comes back into this receiver. So this preclinical polarizer still uses the same fluid path that is used for clinical studies in the spin lab. The probe is very flexible, so it's a very more modular, and researchers can change the probe for doing cross-polarization and transfer polarization between different nuclear spins and so on. One of the key things of such a system like this one is that we cannot impose very strong heat loads. So this vial is infused through an airlock into the helium space so that we do not impose too much heat load on the helium. And you see here an example of the sample introduction that does not heat the bath by more than a few tenths of millikelvin. And also during the dissolution where we inject the boiling hot water, the temperature does not rise very much. So it is really a challenging cryogenic system, but by some smart engineering and cryogenics, we can actually combine this very low temperature space with injecting hot boiling solvent into a cryogenic space. Yes, it's also very flexible. A dry magnet like what I just showed you, it's very easy to energize, put it at field, take it off field. And for DNP and studying the physics of dynamic nuclear pulsation, it's very nice to operate at different field strength. So this system is also very flexible, that it's easy to change the field. And as we change the field, we also need to change the microwave frequency, the frequency where we irradiate the electron spin. So the way I have preferred to do it is to use an oscillator at 94 gigahertz, and then just use doublers and triplers to go to higher frequencies, and then we can do studies at 3 Tesla, 7 Tesla, 10 Tesla. And the probe that I showed you in the previous slide is really broadband, so all the microwaves will propagate to the sample and be scattered and irradiate the sample. So it's really broadband, so in less than 10 minutes you can change configuration quite easily to do multi-field studies. The polarizer is operating best at 6.7 Tesla, as I'll show in this study. One of the first things we did was to investigate pyruvate, which is the most studied molecule, with the tridal, which is the radical that performs best. And one of the things we learned of these new high field studies is that as we go to higher field strength, the resonance frequency, the Lama frequency of carbon, of course, scales linearly, but the line width of the radical also scales with the field, but the broadening, the G anisotropy of the radical is not large enough to give us the line width of the radical that we need to have good DNP. So you can see here that the line width of the radical becomes less than the Lama frequency of the carbon, and therefore we do not get the high DNP efficiency that we expect. So really, when we go to from 3 to 6 to 7 Tesla, the polarization at 10 Tesla is no better than we have at 6.7 Tesla, so there's no reason to go to high field, and it's really due to this fact that the EPR line width is not broadening in the same way. This slide just illustrates that DNP is a slow mechanism, so it takes a long time to polarize in the solid state, 1 hour, 2 hours. So we really have to optimize the concentration of its electron spin, the microwave power, how we irradiate to get the best possible DNP effect. But we can reach almost full polarization, more than 50% polarization in general, as you can see here, and with a time constant of under optimized condition of maybe 20 minutes. So it really should be compatible with the throughput that we need for animal and patient studies. but it is slow with DNP, and we need to still work on ways of optimizing and improving the throughput of DNP. Sure. I hope I convinced you that the technology can be simplified in a way that it's manageable and can be used in a clinical practice. I think the cryogen-free technology is well suited for dissolution DNP, that we can reach very high polarization. We can actually polarize different biomolecules to a very high degree in a reasonable time. Yes, okay, so now I want to change, in the last part, I want to talk about as well two things that are really something that we have been pushing a lot. This is Copenhagen, this is a map of Copenhagen, if you're not familiar with it. My university is there, roughly. So and it's not really our ideas, a lot of people have been thinking about this, but what if we could avoid having this complicated polarizer technology? If we could liberate the polarization from the instrumentation and we could just provide hyperpolarized substrates to the clinic or to the point of use in a similar way as nuclear tracers are distributed in a certain region. So let's imagine that we had a polarizer somewhere here, and that we then have users around the in the region, and then we polarize, and then we have a kind of a service operation that could then drive around to the local hospitals and deliver the hyperpolarized substrate. That would be a very, very nice idea. So this should in principle be possible, and there have been many suggestions, or several suggestions, of how that can be done. The approach that we have taken is a recent idea that came from EPFL, actually. The challenge is that the radical that we use for the DNP to polarize is also the source of relaxation afterwards. So in order to be able to extract the polarized solid out of the polarizer and distribute it with a long decay time, we need to get rid of the radicals in some way. So the idea here is that we can actually generate these radicals optically, photoexcite some precursor to generate a radical spin or an electron spin that is stable under certain conditions, and then we can annihilate that electron spin in some way. And this is shown here that by selection of a proper precursor, we can, at low temperature, could be liquid nitrogen, we can photoexcite the molecule and generate a stable free radical that gives an EPR spectrum that is suitable for DNP. You see here an example of that, and you can see that we turn on the microwaves, we start to polarize the nuclear spins, the carbon-13. If we turn off the microwaves, then it decays back to some equilibrium. You can see that this time constant is not very different, and that it comes back to some equilibrium very fast with a time constant of tens of minutes due to the radical. But if we briefly heat the polarized sample to some temperature while still in the solid state, these radicals will annihilate, they will quench, and now we get a radical-free solid, no EPR spectrum, and the relaxation time is now much longer, and on the order of 12 to 24 hours, practical for distribution of the solid polarized sample, and now we can extract it from the polarizer. And one good example of a precursor turns out to be actually pyruvate, our favorite biological molecule. So if you take pyruvic acid, which is the keto acid, then it absorbs at 320 nanometer. You can excite one of these bonding electrons to a triplet state, and by intersystem crossing, it will relax back through a triplet state to the ground state, and decompose into a stable radical, a radical that is stable at a low temperature. So we end up with this lactyl radical, the unpaired electron, which gives this EPR spectrum, and which is suitable for DNP. We can also change the EPR properties of this radical. You can see here that if we take the pyruvic acid, it gives an EPR signal, but if we introduce hyperfine couplings due to carbon enrichment, we can either broaden the signal or we can remove hyperfine couplings to the protons to get a more narrow EPR spectrum. So we can also shape the EPR spectrum in order to get the best possible DNP efficiency. These radicals are stable at liquid nitrogen temperatures, and we can quench them if we raise the temperature of the sample about 200 Kelvin. So that's the temperature that's close to the glass transition of this solid material, and it becomes mobility, and they will quench, annihilate, and go away. This is still a solid sample, so we can briefly raise the temperature to 200 Kelvin. These radicals will go away, and then we can cool it down again. In the case of pyruvate, the degradation product of that is relatively benign, so that's also quite nice. It simply decomposes into CO2 and acetate. So from a biological point of view, it's also a very neat example.
Is that 18-hour half-life at 4.2 K?
Yes, that was 7 Tesla for 4 Kelvin. Now, of course, for us, one of the questions been is pyruvic acid the best precursor for DNP? Because if we look at the tridal, which is the radical we use for getting these more than 50% polarization, then it has a certain EPR spectrum line width. The radical of pyruvic acid is broader, it's shown here in black. And if we compare to the Larmor frequency of carbon, then the tridal is good because it's perfectly matched to the Larmor frequency of carbon. The pyruvate radical is, you can see, much broader, and we have electron spins that resonate too far away and does not contribute to DNP. I'm just pointing out here with the proton Larmor frequency, which is 4 times higher, and you can see that that's much wider than the tridal resonance frequency. So tridal is not very good for proton DNP, where the radical that we generate from pyruvate is much better matched to that, but maybe on the narrow side. So if this black EPR spectrum, if we somehow could manipulate that, make it more narrow for carbon polarization or wider for proton polarization, that would be really neat. And I already indicated that that is possible by introducing broadening mechanisms, hyperfine couplings. So if we take the pyruvic acid here, then we can remove the hyperfine couplings from the protons to get a more narrow, either by deuteration or methyl groups. And then we can get an EPR line width, which is much closer to the tridal line width and gives very good DNP, better DNP. And maybe you also noticed on the example or from the EPFL data, the original data, that the build-up curves, the polarization that was generated in the solid state was not the 70% that I showed earlier, but when we went to something like 4 or 5%. There really is, we really need to improve on the DNP efficiency to match the tridal frequency. We spent a lot of time both optimizing the radical yield and creating these more narrow-line EPR precursors. And here we see an example of not pyruvate polarization, but are showing that we can polarize other things. Pyruvate is still the precursor for the UV-generated radical, but the substrate of interest here is glucose, which is also a molecule that we use quite a lot in both in vivo and in vitro metabolic studies. And here you see that if we compare to the tridal, which gives a decent polarization, not quite the 70, but 40% polarization, then these UV precursors actually exceed and give just as good polarization, and we can get, in the case of glucose, almost 50% polarization. Glucose has a shorter T1 than the pyruvate, so you can see also that the T1 of the C13 of glucose is a bit shorter, 15 to 20 second T1s, but long enough for us to introduce it into an animal and see pyruvate degradation all the way through glycolysis. Now, this is, I'm switching a bit away from the metabolism where we need the carbon-labeled molecules, but one thing that I personally have been very interested in is using hyperpolarized water as a contrast agent for angiography and perfusion studies. The proton is, of course, our preferred nucleus from a sensitivity point of view. It has a large magnetic moment. It's good in terms of, due to the large geometry ratio, it gives, it's easier for high resolution imaging. all the MR scanners and coils sequences are optimized for proton imaging, so it's already there. We need more signal to get higher resolution images for angiography, and we can use the water as a, let's say, the ideal perfusion agent. Hyperpolarized water has some interest also in NMR spectroscopy to look at the proton exchange, water exchange, hydration reactions, especially in proteins, but also in chemical reactions. So there's been a lot of interest in using hyperpolarized water for that reason. My interest is more for the imaging and medical applications. Oops. Oh. Yes, so other people have also looked at that, so there's been interest historically for that. Now, we could use the dissolution DNP to hyperpolarize the water protons, and just again highlighting that, or indicating that if we take our the signal that we have available in the MR scanner, then yes, we have maybe 60, 80 molar of water protons in the body. When we put the patient in the 3 Tesla, we could polarize those protons to 10 ppm, so we can calculate the magnetization that we have available for imaging. Now, if we could hyperpolarize protons, then, well, we can maybe get to the same polarization degrees as I showed with carbon-13, so 50%. Now and I'll qualify that. We reduce the concentration. We have to do that for various reasons. But still, if we go down to an order of magnitude in concentration, the product of concentration and polarization still gives us a magnetization which is almost, well, it's more than 1,000-fold bigger than the magnetization that we have available. So we could have a huge signal for anatomical imaging with hyperpolarized water. So that's the theory. In practice, we need to do something about the T1 because we know that the water proton T1 is very short, it's a few seconds, so that's the challenge. That's too short for hyperpolarization in any practical sense, but we can actually increase the T1 of the water protons by diluting the protons in D2O. So here I show you that, neat water has a T1 of 3 seconds, tissue shorter than that, 1 second. But if we increase temperature or dilute the protons in D2O, 10%, 5%, then the T1s can actually become very long and comparable to the carbon-13. So that's the reason we reduce the concentration, we dilute in D2O, but we can actually get T1s that are relatively long. The challenge is that we have a radical, which is used for the DNP. When we do the dissolution, the radical is normally there. Carbon-13 is not affected by the presence of the radical, so normally we leave it there, but protons are much more affected by the presence of a paramagnetic agent. So to get these T1s, we also need to get rid of the radical after the dissolution. And now you can see that the UV radicals become, again, very opportune. There are other ways of doing this, and our first work, so I'll give a couple of examples of, we actually use the stable organic radicals, but then in order to get rid of them, people have suggested to either use a two-phase system, extract the radical into an organic phase, or try to quench the paramagnetic agent with ascorbic acid or some other reducing agent, so chemically reducing it to some diamagnetic molecule and get rid of that relaxation effect. So that is what we did initially. This is how this was done. So actually we hyperpolarized the water by dissolution DNP, extracted the radical into an organic phase, and by that method we were able to get about 200 times stronger magnetization than the thermal water signal, not quite the 1500, but very strong signal. And you see it here, you see the hyperpolarized signal. You see after 200 seconds where the hyperpolarized signal has decayed away into the noise. We see the lobe ring and the thermal phantoms, but really 200 times bigger magnetization, which corresponds to about 5% polarization, and a really strong signal that enables us to do angiography and perfusion. This was done very crude. This is just an example of intraarterial injection of hyperpolarized water. So now, because of the short T1, when the hyperpolarized water T1 is long when it comes out of the polarizer, but when it mixes with the blood, the T1 is reduced very quickly because it mixes with the blood. It goes down to a second, so we have to do intraarterial injections. Here's the injection in the coronary artery. It's just a free running, free breathing, not optimized from an MR point of view, but still we were able to get very nice angiograms with this level of polarization at that time. So now we have looked into using the UV radical for the polarization, and as I mentioned, by introducing hyperfine couplings, we can broaden the EPR spectrum of the radical to a point that it becomes optimal for dissolution DNP. This is just illustrating how it's done. We can take our water. We need to add some glassing agent to get an amorphous sample. We put the precursor, the pyruvic acid, C2 labeled, because that gives us the right EPR spectrum. We freeze droplet in liquid nitrogen, so we get nice transparent beads. We can then irradiate those beads with UV light to generate the radicals, and they change slight color. And then we have a high concentration of radicals in these beads. We can then transfer these beads from the liquid nitrogen into our sample cup and introduce them into the polarizer and turn on the microwaves to irradiate and get DNP enhancement. Just as a reference to what I showed you earlier with the stable free radicals, this is the polarization we get, that in the solid state we could get with stable free radicals, like the nitroxide here, high polarization in the solid state. If we just use pyruvic acid, well, the EPR spectrum is not really good, so we don't get the high polarization and it's slow. But if we do the broaden the EPR spectrum a bit, then we can get similar solid state polarization, almost 80%. And if we dilute the protons in the solid state a bit, we can almost get to unity polarization. So we can really create an almost fully polarized protons. And then we can have to dissolve them. So we have here in our polarizer, we have the hyperpolarized water sample. And we dissolve it in D2O, which have been degassed because oxygen is also paramagnetic. We heat it to a high temperature, and then we push with helium gas. We can push the sample to our NF spectrometer. So there we put our sample, and then we are ready to do the dissolution and injection. So we take the D2O, heat it to the 200 degrees, and dissolve through the inlet tube, and the hot water sprays on the sample and dissolves the solid sample very quickly. The D2O, the water protons come out and run to the NMR spectrometer, and we acquire an NMR spectrum. So this is just the same solid state data that you saw before. Polarizes very well in the solid state to almost 80 to 100%. Before, with the stable free radicals, we lost a lot of the polarization and dissolution because of the paramagnetism of that. So that's the reason we only got 200 times more magnetization in the previous example. But with the UV radicals that quench in the dissolution, we can actually almost fully preserve that nuclear polarization in the dissolution. So now we end up with 50 to 70% nuclear polarization, even by very high concentrations of protons. So really a huge magnetization that really gets close to those 1,000 times to 1,500 times the thermal water. Yes, so in summary of all I've been saying is that I hope I have convinced you that the hyperpolarized MR adds something to the anatomical MRI that we are doing, that we can actually use hyperpolarized metabolic MR to characterize disease. So we get biological information, biochemical information that helps us in terms of stage disease, monitor response to treatment. That MR, as you're fully aware, provides a lot of beautiful anatomical information, but also spares the patient of any ionizing radiation. That we have been able to translate this now to the clinic. So people are now doing clinical studies at various sites. That we have a polarizer technology that is practical and can fit into a clinical work practice. And that we even may be able to distribute hyperpolarized substrates to different points of use. And liberate the hyperpolarization from the infrastructure. And then I would like to thank you for your attention and acknowledge my collaborators and my group for all of the work that I showed you. So thank you very much.